Dear everyone, welcome to our work unit, Unifying Tensorized Instruction Compilation. This work is accepted by CGO 2021, and it's a collaborative work between UCLA and AWS. This work is aimed at providing a unified compilation flow for the instructions with tensorization idiom. Unlike conventional SIMD, this idiom is no longer element-wise. Multiple input lengths with lower precision are reduced to output lengths with higher precision. As it's shown on the right-hand side, Intel performs 16 8-bit dot products and produces 32-bit results. NVIDIA Tensor Core performs a 16 by 16 by 16 FP16 matrix multiplication, and the results are FP32. This idiom widely exists in quantized and mixed precision DNN models. However, the high-level abstraction for these instructions is still absent. Prior work either develops specialized compilers for each single instruction or manually writes hardware intrinsics. Neither is satisfying in terms of extensibility and productivity. We achieve the best of both extensibility and productivity by presenting a unified compilation flow for tensorized instructions. Instead of building a specialized compiler for each instruction, we take the semantics of the instruction also as an input to the compiler, so that the compiler can take advantage of this semantics to analyze the applicability and guide the code transformation. In the rest of my talk, I will walk through each step of the compilation flow. We use the TVM tensor expression DSL to describe the semantics of each instruction. As it's shown on the right-hand side, the computation behaviors are described in a TEOP, and each input tensor of this OP is regarded as register length. The computational expression loop axis and the input tensors of this OP will be used to analyze the applicability of this instruction on a given program. I will next demonstrate how Vini is analyzed and applied on a 2D convolution. The applicability analysis is separated into two phases, the computation and the data access. In the computation phase, it checks if the arithmetic operations performed by the instruction is the same as the tensor program. Not only the operation, but also the data type should match. The data type cannot be implicitly cast because of the nature of mixed precision. In this case, the instruction and the convolution operator have exactly the same expression tree, so we pass this phase. Instead of defining everything formally, here I just give an intuitive explanation to the memory phase. We enumerate a subset of the loop axis to be tensorized, as is shown in the right-hand side. We choose loop K and the loop C. They are tiled and reordered to get ready for tensorization. However, do remember, for now this code reorganization is still hypothetical. This will not be finalized until the feasibility is checked. To check the memory feasibility, we require each register length in the instruction only corresponds to one scalar memory operation under the gray region. If not, we should try another mapping. We enumerate this loop axis from the inner to outer greedily and return the first feasible one, since the inner loop axis potentially have better data locality. The last piece of compilation is code generation. As I mentioned before, the innermost tiled loops will be offloaded to tensorize the instruction. We expose the memory access patterns of each memory operation in the loop body and leave it for the compiler developers to decide how to prepare each operand of the intrinsic call. Then the innermost loops will be replaced by this intrinsic call. The outer loops are still open to performance tuning. We have strategies for this, but for the sake of time, we don't discuss this in detail for now. Finally, we come to the performance. Here, we run 9 classic DNN models with batch size 1 on both CPU and GPU. The tensorized instruction rewriting accompanied with our tuning strategy can outperform these highly optimized vendor-provided libraries like 1DNN and cuDNN by 1.3 and 1.75. To conclude our work, we provide a unified abstraction to integrate the new instructions easily, a unified analysis path to automatically detect the applicability and reorganize the loops, and a unified interface for code generation. For future work, we have two directions. One is to relax the constraints of this detection. For example, pooling layers can also take advantages of Vini, but one of the operands should be all ones. The other is to integrate this to rule-based auto-scheduling like answer.